Okay, new chapter, all about nutrition. So in the last chapter, we talked about digestion, where we took our foods and broke them down into an absorbable form. Now for this chapter, we're going to look at those monomer building blocks. What happens when we actually start using them in the body? So we've actually absorbed them, now what? So that's what this chapter is going to be, is taking those monomer building blocks and using them. So in the first question on the study guide, I talk about this slide, the macronutrient storage and ATP pathways. So with our digestion, we talked about carbohydrates, fats or lipids, and protein. So this, I know it looks like a lot, but this actually contains almost most of what we're going to cover in this chapter. So we're going to look at our carbohydrates. So there's our glucose monomer. So how we actually take glucose, break it down, and eventually extract the energy out to make ATP. So as you can see, we got arrows, they're going in different directions. So we can break down glucose, but then we can also take it and go back to glucose. We can go back and forth with the storage of glucose. We have our fats. They technically could have been on one side, but just for the prettiness of this, they're all the way across. So stored triglycerides, breaking them down, using them in our pathway to make ATP, or repackaging them and turning them into triglycerides again, or taking these triglycerides, breaking them down. We actually can take pieces of them and make them into ketones that we can use to also make more our non-essential amino acids. So some amino acids we do have to get from the diet. And then later we'll talk about our amino acids. So from our protein, taking them, breaking them down, either using them back as non-essential amino acids or putting them also into our system for eventually making ATP. So we're actually going to go over all of this step by step, and you'll actually learn all of this. It's going to take some time to cover everything. So we do break down everything. So the second one, I left it as a way to, how do I say this? Like, it's kind of used as a practice. So you have the word banks of where stuff should go. And that way you can edit the slide, like, of course, you download the PowerPoint and, can remove the words from wherever it is. And that way you can test yourself of, okay, do I know these different pathways? Because we're actually going to cover every single one of how these different things work. Okay, so let's talk about nutrition. So looking at our different nutrients and how they can stored or be used in different ways. So let's talk about appetite. So actually getting the urge or to actually eat. So part of our digestive system's function is to communicate with the brain on the activity that's going on in the digestive system. So telling the brain, hey, it's time to eat, or nope, we've received enough food, so it's time to stop eating. So in order to do that, it uses the gut-brain peptides. So these are hormones, so they're secreted into the bloodstream, and they go from our gastrointestinal tract, eventually traveling to the brain to tell our brain whether or not to have the feeling of needing food or, okay, you've had enough. So when these gut-brain peptides reach the brain, they're going to trigger either the release of an appetite stimulus so that you are encouraged to eat, or an appetite inhibitor so that you are discouraged from eating. So that kind of full feeling. So with our hormones, they can either control short or long-term appetite. So you actually have those charts that are in the study guide where you fill them in. So this is what we're talking about. So for our short-term regulators, they work during an actual meal time. So only minutes to hours around a meal time. So either they're going to make you feel hungry so that you actually start eating, or feel sated, or as in that kind of full feeling so that you stop eating. Our long-term regulators are going to work for weeks to years. So looking at the storage of your nutrients and whether or not, hey, you need more of a certain thing. And so continuously increasing the amount of, let's say, if, your fat levels start dwindling down. And so it's going to actually encourage you to eat because it's like, hey, that's going away. And of course, our body, we, millions of years of development through ice ages and famines. And so we hold on to everything except for amino acids. Who knew? Okay. So our short-term regulators of appetite, we have ghrelin, peptid YY, amylin, and cholecystokinin. So ghrelin, that is released from the parietal cells when your stomach is empty. Basically, feed me. There's nothing here for me to do. I'm bored. So this gives you the sensation of hunger, and therefore also helping you to eat so you can actually fill the stomach up. It's also going to stimulate the release of growth hormone. So as you are eating, you're going to be putting in nutrients into the body, and so your body can use them to grow. So your ghrelin secretion ceases within an hour of eating. So that's why another thing that I say, take your time eating, because you're going to get these different signals and they take time with giving the response back and forth from your digestive system. The next short-term regulator is peptid YY or PYY. A lot of times you'll see that as short. So this is released from our enteroendocrine cells of the ileum and the colon. So the ileum being in your small intestines and then your colon being your large intestines. So these are able to sense that food has arrived in the stomach. So they're going to signal satiety and help you to terminate eating. Again, it takes a while for these to release their products. So that's why, if you scarf down your meal and you're like, man, I'm still hungry. It's because you still have that kind of time gap between, yes, you've actually eaten and your brain actually knows that. Other ones, so cholecystokinin, so CCK for short, so released by the enteroendocrine cells in the small intestines, stimulating the secretion of bile and pancreatic enzymes. This is also a appetite suppression. So as you have filled the stomach is digesting, we're starting breaking down stuff. Stuff is going into our small intestines. You're like, okay, we should have enough food. We're good. We're digesting stuff. We're moving stuff along. So yeah, you can stop eating now. And then the last one, amylin from the beta cells of the pancreas. So again, as you are releasing your pancrease enzymes, all those juices, when you get that signal of, okay, yeah, we've actually are starting this whole digestion thing. We've actually got some food in the body, so we can stop eating and inhibit the stomach activity because you have done your job of breaking down the solid food into the liquid kind. Long-term regulators. So leptin and insulin both tell the brain how much fat we have or how much adipose you have. So they're going to activate your brain in order to adjust your feeding, either to add fat or reduce fat. So depending on how much your level is, if those levels drop, your brain knows, hey, we don't have as much fat. We must need to eat more. So your body's always working against you about, if you're trying to stay healthy and fit, yeah, you're fighting against a lot. Okay, so leptin is secreted by the adipocytes. So again, the fat cells. So it is proportionate to your fat store. So more fat, more leptin. Less fat, less leptin. So again, tells the body how much fat we have. So for some people who are obese, a lot of them, the reason why they're obese is because they have defective leptin receptors. So your fat cells are producing the leptin levels and appropriate amounts to tell the brain, hey, we got enough fat. But because the receptor isn't binding to the leptin, so there isn't that lock and key signal, so the brain knows, oh, we got enough fat, because the brain doesn't get that signal, then the brain continues to have the input of, oh, we still must need to eat because we don't have enough fat cells. It's just because the brain's just not getting that signal. The other one is insulin. So this is secreted by the pancreas. So when you eat and you gain glucose is part of your meal, then that stimulates the release of insulin. So it tells your cells to take up glucose from the bloodstream as well as take up amino acids. Insulin's also going to promote glycogen and fat synthesis as you are taking in glucose. So we need to store that glucose as glycogen, and any excess that we don't need, we also can store it as a triglyceride or a fat. So going back to that first slide for this chapter, yeah, there's a lot of arrows going back and forth. So there are ways to convert the different molecules into each other. So when these peptides reach the brain, again, they're either going to stimulate appetite or inhibit it. So let's look at our nutrients. So a nutrient is defined as any ingested chemical used for growth, repair, or maintenance of the body. So basically any building block you can use in order to keep your body maintenance up. So we have 6 classes of nutrients. They are broken down into 2 different classes. We have our macronutrients and the micronutrients. The macronutrients, so macro as in big picture, are the types of nutrients that we need in large amounts. So water, drink your water. Okay, off the soapbox. Okay, so water, carbohydrates, lipids, and proteins. Versus vitamins and minerals, which are micronutrients, so very tiny amounts that we need. So it kind of the difference between, we eat multiple times a day, full meals to get our macronutrients, but then the micronutrients, we can take a little small pill for our vitamins and be done. Okay, so let's focus first on the carbohydrates. Excuse me. So sugars can work as a structural component for our different parts of the body. Most of our sugars or carbohydrates, when they're broken down, they're easily oxidized for our source of chemical energy. So broken down so we can make ATP. So most of our cells can use a combination of carbs and fats in order to meet the energy needs. So either using either one of them in order to make ATP. So most cells are flexible in whatever fuel source that they can use in order to make ATP. However, your neurons, so your brain cells and nerve cells, as well as your erythrocytes or red blood cells, only use carbohydrates, particularly glucose, as its fuel source. So it's not as flexible as your other cells. So with our glucose levels in the blood, or plasma glucose, another way of saying this is blood sugar, that's closely regulated in order to maintain certain levels, because especially for more so the brain than the red blood cells, making sure that those cells have enough glucose always is going to be regulated. So that's why a lot of times when you're studying and you're using a lot of brain power and all of a sudden you're like, man, I want a snack. It's because your brain is like, we're using a bunch of glucose because we're working hard. You need to go eat a snack so we can boost up those glucose levels in the blood and I can have whatever I need. Essentially, that's how that works. Okay, so with our blood glucose level, so part of that is regulated by insulin. So, of course, you probably all know someone who has diabetes and has to use insulin as a regulator for that. So, by adding insulin, because they're either deficient in making it or they become less responsive to it. So that insulin is going to decrease the blood sugar because you have eaten something. So that insulin's going to regulate as it, hey, get this blood sugar into the cells so that we can decrease our blood sugar levels. While glucagon is going to increase blood sugar levels. So breaking down the stored fuels so that you can have enough glucose inside the bloodstreams for these cells whenever they need it. So this is going to regulate between our glycogen, which is our stored glucose, and the free glucose that's hanging around in our plasma. So depending on how many carbs you take in, it's going to influence the breakdown of your other nutrients. So if, let's say, you go on a low-carb diet, that's when you start having to use your fats as fuel because your glucose and glycogen levels are low. So because your body eventually is going to use up that sugar because you no longer are taking sugar in because of your low-carb diet, that's where you have to switch to fats as a fuel source and saving as much whatever glucose you do get in that low-carb diet, reserving that glucose for your red blood cells as well as your brain. Any kind of excess of carbohydrates, instead of going low, we're going too much. So those are converted to fat. So hey, we can store this up. I mean, granted, you can balance out your blood sugar levels, but eventually it's like, okay, we've got too much. Let's store it as fat and know where we keep it. Again, our bodies develop during times of famine, so we're stuck with that memory. Okay, so we have carbohydrates that come in 3 principal forms. Basically, how many monomer building blocks are attached to this carbohydrate. So our first one are the monosaccharides, so mono meaning 1. That's glucose, galactose, and fructose. So again, 1 monomer building blocks for them. So this is breaking down of starch and disaccharides to make these monosaccharides. So the small intestines and the liver can convert both the galactose and fructose back into glucose, because that's the form of sugar that we use for making our ATP. Ultimately, all carbohydrates going to generate glucose. So whatever you get broken down to, either you get broken down to glucose, or it's in another form where you can convert it into glucose thanks to our small intestine and the liver, who's doing yet another job. Okay, next crew is disaccharide, di meaning 2. So that is sucrose, which is our table sugar, as well as maltose, which is found in grain, and lactose, which is found in milk. So people who are lactose intolerant, they no longer create the enzyme to break down that milk sugar. Then our last one are polysaccharides. These are complex carbohydrates that eventually they got to get broken down and digested. So starch, glycogen, and cellulose, which although it is a carbohydrate that we eat, we don't have the enzyme to break it down. So that's why I have to rely on the gut microbiome, so our gut bacteria, to break down the cellulose into essentially a little small fiber strips so we can at least line our digestive system and keep everything flowing, particularly our large intestines. So essentially breaking it down so you can have your roughage, if you're older country enough to know what this is or have relatives, roughage. Getting your fiber in there to keeping you regular. So speaking of fiber, so fiber is the only thing that we take in that resists digestion. So we got 2 different types. We have water-soluble fiber, such as pectin, which can be found like in fruits, and different other like plant sources. So this type of fiber, which is why you see on a lot of your cereals, will say it decreases blood cholesterol and LDL levels, which will make sense later. Basically, you want those levels to be low. So that's why they put that on their packaging. But this fiber does help to absorb that. And then your water-insoluble fiber, so it's not going to break down in water. That's cellulose and hemicellulose and lignin. No effect on our cholesterol and LDL levels, but their job is to absorb water in the intestines. Basically, this is going to help line everything, keep everything going. So getting your fiber in, that kind of fiber. Helps to soften the stool, so helping to making sure that it's going to go ahead and pass. Helps to stretch out the colon, stimulate peristalsis, so moving the feces forward so you don't end up with a constipation. That's it. Yeah. So keeping you regular. Okay, moving on to lipids or the fats. So most of our resting energy needs come from fat. With our fatty acids, fat is superior to carbs for energy storage. So it takes less processing of our fats in order to break them down in order to extract out energy. So actually, let's do that. Let's go back to that chart. So if we're comparing glucose to our lipids, so here's our glucose. We got to go through this whole process of glycolysis to break down the glucose before we even get to our citric acid cycle and electron transport chain in the mitochondria in order to extract out the energy. However, for our triglycerides, we can break off a piece of fatty acid, so using 2 of the carbons, what's called beta oxidation. Take those little pieces, attach it to an acetyl-CoA, and then shift it right into our ATP production. So here you only got, breaking off a piece of the fatty acid, sending it, attaching it to this molecule, and then going, versus here you got to do all this processing. And then if you just happen to have enough, well, you have to have oxygen for both of them, but long process to get there versus here, break it off and then go straight there. So just a little bit easier. Plus, you can keep breaking off pieces off of that fatty acid to continue to make ATP versus glucose. You got to do this whole process all over again. So one molecule of glucose versus one molecule of triglycerides, and you just keep breaking off stuff in order to make ATP. So you have more opportunities to make ATP with a triglyceride than with glucose. Okay, other benefits of using fat versus carbohydrates for energy is easier to store it. Since carbohydrates are hydrophilic, they're going to absorb water, and so they're going to bloat up and take more energy, more space, versus fat being hydrophobic, and so it's going to be more compact. Plus, again, fat contains more energy than a carbohydrate molecule because there's less processing you have to do in order to get it out of there. Oops, other direction. Okay. So, with fat, it's also glucose sparing, so your other cells that can be flexible and use other sources other than glucose, they can use fat, while your brain cells and red blood cells can use glucose instead. So, helping to spare that for those cells, as well as being protein sparing, because going back to our little chart, you can also break down proteins and also use them in order to make ATP. So preventing our protein from being catabolized for fuel. So if you ever seen, sometimes older people when they've kind of they're ready to go and so they don't eat as much and so their muscles start breaking down. That's the same thing. The proteins start getting broken down and used as fuel. Another benefit of our lipids is they're necessary for absorbing some of our vitamins. So A, D, E, and K are the fat-soluble vitamins. So in order to take advantage of these vitamins that you have taken in as part of your nutrition, so whatever you're eating, making sure that you have fat as part of that, as part of your meal, that helps you to be able to absorb those fat-soluble vitamins, because if not, then they're just not going to be able to be absorbed. Okay, so functions of lipids. So structural with our phospholipids, making our cells, as well as cholesterol, helping to maintain plasma membrane stability. They're also a precursor for other molecules. So cholesterol being the parent molecule for steroids, as well as biles. Thromboplastin, which is necessary for blood clotting. Different fatty acids, which can then be used as signaling molecules, and helps with protecting the body and insulating the body. Basically, all that fat tissue around your body. So, fat butt, you fall on it, you have good cushion. Okay. So, sources of our lipids. So, we have our saturated fats. These are our mostly animal fats, and you do have some in coconut and palm oils. Your unsaturated fat are mostly your vegetable or plant-based fats. And then you have cholesterol from egg yolks, so the yellow part of an egg. Cream, which is which is animal origin, like dairy. Shellfish, different organ meats. So if you ever eat the liver or the heart of an animal, like deer, will have a fair amount of cholesterol in there. But only very trace amounts in plant-based fat sources. Okay, so we're going to start a new video on this one. See ya!